So thank you for the introduction. So this is joint work. So this is joint work with Peter Müller and Alex Sommer. Before going to unbounded separation logic, let me start by introducing or reintroducing separation logic and the frame rules, so the basics. So separation logic is an extension of our logic designed to reason about programs that manipulate the heap. And as an example here, we have a method caller that allocates a new object f with a value 5. So what this does, it simply creates an object with a field f and a.f is 5. Similarly, we create a new object f with a value 7 and assign it to b. And then we have a method call here to callee with b. The implementation of callee is not shown on the right, but we just know that it reads b.f. And finally, at the end of the program, we want to show that here a.f is 5 and b.f is 7. So we just want to prove here that these values were not modified. And the way separation logic handles this is by associating permissions with heap location. So at the start, we have no permission, we have an empty context. And once we allocate a new object and assign it to f, we get this permission here to a.f. So this represents an exclusive permission or a full permission, and this permits to read and to write a.f. And this is typically written in separation logic as a.f points to some value. Similarly, we allocate a new object in B and we get another permission, b.f. And here it is, because we have permission to both a.f and b.f in separation logic, we know that a and b cannot be aliases. Otherwise, we would have too much permission to the same heap location. So now we want to reason about the call to callee, and in particular, we want to prove that callee does not modify a.f or b.f. And to reason about method calls, we want to do it modularly. So we need to give a specification to callee. And in this specification, we need to give, as a precondition, permission to b.f, because callee needs permission to read b.f. And in the post condition, we give back the permission to b.f, such that the permission is transferred back from the callee to the caller. So to do that, to reason about method calls, we use the frame rule that was already shown in the previous talk. So the frame rule is crucial for local reasoning in separation logic. It says that if we prove that some command C holds under precondition P and results in precondition P and results in postcondition Q, and in our case, P is the precondition of the method, Q is the postcondition of the method, and C is the method body, then it will hold in a larger context here. The execution of the method will hold in a context where we have P star R, and the star here enforces that the permissions are disjoint. So R is typically called the frame here, and in our example, R corresponds to the permissions that are not given, that are not transferred to the callee. So this is a.f, and a.f is kept by the caller during the method call. On the other hand, permission to b.f, because this is asked by the precondition, is transferred to the method callee, and this is transferred back from the post condition to the caller. And now using that, we can actually prove that a.f is still 5, and the reason is that callee couldn't have possibly modified a.f because callee never had the permission. The callers always had the permission to a.f. But here, our specification is a bit too weak. We cannot prove that b.f has not been modified, and this is because of the specification here of callee. Even though callee only reads b.f, we do modular reasoning, and the precondition of callee says that callee has the right to modify b.f. So this shows that the specification is too weak, and to do that, to give a stronger specification, we can use fractional permissions. So fractional permissions are an extension in which we have fractions between 0 and 1 that can act as permission. So in this case, we can give as the precondition and postcondition of callee only half permission. So this permits only reading, because some other threads or some other context might have another fraction to this heap location. And this is typically written as b.f here points to some value with the permission amount on top of it. And now that we have this, we split in our context permission to b.f into two fractions here. And now our frame is larger. Our frame contains permission to b.f. So we still apply the frame rule like this, but now we know that b.f couldn't have been modified because the caller kept some permission. So this is the general idea for fractional permissions. And just to understand a bit more what fractional permissions are, it's kind of a fictitious story in separation logic that we have. So it's, if you have a normal program, a normal semantics, you would have a state that is just a partial map from heap locations to values to represent the heap. But for fractional permissions, we extend this state with this notion of fractional permissions that we can see here. So permissions, fractional numbers between 0 and 1. So now, so far so good, but fractional permissions only work with heap locations. But we want to reason about more complicated data structures, such as a binary tree here. So where we have a value x.val on the heap, but also x.left that points to a left subtree, x.right that points to a right subtree. And we can express permission to all of the nodes of the tree here using an inductive predicates, where this definition at the bottom just says that we have permission to x.val, we have permission to x.left, and x.left points to a value, and we also own the left subtree. Similarly, we have permissions to x.right, and we have permission to the right subtree. But this is what we call an exclusive resource, because this is like the full permission before it permits to read and write nodes. But if we want to just specify read access, for example, in a concurrent program in order to share a data structure, this is too strong, too weak, sorry. So we want to use the same kind of trick to have fractional permissions, but to a data structure. So that would look like this. The same tree, except we have only half permission to each heap location in the tree, which permits only to read nodes. And this is what we call in this work a fractional resource, and we write it like this. So this corresponds to 0.5 times the tree, or half of a tree. So why should we care about this, and how do we use fractional resources? So on top of separation logic is also powerful to reason about concurrency in a modular setting. So to reason locally about each thread. And to show, and here I'm showing a simple artificial example. This program doesn't really do anything complicated and anything useful. It just takes a reference X to a tree here. And as long as the tree is not null, it forks two threads. So these two lines here represents the parallel composition. And each thread does the same thing. We print the value x.val, and we recursively process the left subtree and the right subtree. So because the two threads are the same, I'm just going to ignore the right thread here, and instead try to show a visualization of what is happening in the memory, in our representation of the memory. And we simply want to prove that with pi permission, so fraction pi to tree of x, this program is memory safe, and we don't lose any permission. And at the end, we still have the same permission. So this is not something complicated. This is just memory safety. So to do this, we show here the proof outline with OR triples. So we enter the if condition. So we learn that x is not null. And then we want to use the parallel rule of separation logic to reason about the parallel composition. So this is a bit like the frame rule. We can reason modularly about C1 here, and about C2, and then we can conjoin the respective precondition and postcondition using the separating conjunction to reason about the parallel composition. So we have here pi permission to tree of x, and we need to split that into two fractions. So we do this by splitting it into a fraction pi divided by 2 and another fraction pi divided by 2. And then we use the parallel rule to reason locally about the left thread. And the proof for the right thread is the same. So now we have a permission pi divided by 2 to tree of x, and we need to justify that we can read x.value here. And remember, to justify reading, we need some permission. So what we do here, we can unfold the definition of tree of x and distribute this fractional permission pi divided by 2 over each conjunct. And now we have everything to justify here that we can read x.val because we have some non-zero permission to x.val. We can recursively call process tree with x.left, with the left subtree. And in this case, pi here is a ghost parameter that is going to be instantiated with pi divided by 2. And same thing with the right subtree. So then we get back the same permissions, we have the same context, and now we need to revert the process. We need to revert this distribute step and this split step. So the opposite of distribute is factorization. We have pi divided by 2 that is distributed over every conjunct So we factorize it back, and we fold the definition. And then we use the parallel rule to recombine the two post conditions, and we do this fourth step, combine. So this proof looks simple, and it only proves memory safety. And even though this program is a bit artificial, these four steps are typical patterns that are typical steps that we need to perform in typical proofs like this. So split, distribute, factorize, and combine. And so you might ask, okay, what's the problem here? And the main question is this proof outline actually correct? Because it looks nice, we would like to be able to do proofs like this. And the answer is that it depends. It depends on the meaning we give to fractional resources. And there is not one, but actually two different meanings one can give to fractional resources, which is something we discovered in this work. There is what we call the semantic multiplication. This is the intuitive definition, and this is a definition that has been studied in theoretical paper. And with this definition, the previous proof outline is incorrect. The factorized step is actually unsound, so the first step. So in this paper, in this talk, we write it like this. So the notation I've used, a fraction pi of A, and this is the definition. So here, just to remember that a state is a partial map from heap locations to values and permission amount. And we say that H satisfies a fraction pi of A if and only if there exists some other state that satisfies the assertion, and H is a scaled down version of this state by pi. So if you replace A by a tree of X and pi by a half, what this says is that half of a tree is simply a tree where we multiply each permission amount by a half. So this intuitively corresponds to the picture we had before. And there is actually another meaning for fractional resources, and this is what we call the syntactic multiplication. This corresponds to the rules implemented in verifiers based on separation logic, such as very fast or Viper. And with this, the previous proof outline is correct. Or at least with this, we can encode this proof in these automatic verifiers, and the verifiers will verify them. But there is not really, before this work, there was not really a theoretical foundation for why there was this. And I think it was even unclear that these two were different. So the way it works, we write it like this, pi times A, and the way it works is really syntactic. So as an example, if we want to compute 0.5 times permission to L1 star permission to L2, we just take the 0.1, this 0.5, we distribute it over the star. So we have 0.5 times permission to L1 star 0.5 times permission to L2. And then we push it again until we reach permissions here. And we can go back to fractional permissions. And this syntactic multiplication is easy to automate, and the previous proof outline works. So this is something for which we would like to have a theoretical foundation, which brings me to the contributions of this work. So there are these main 5 contributions, but for the rest of this talk, I'm only going to focus on the first 2. So in this work, we discovered this discrepancy between 2 notions of fractional resources that I will explain next. Between the syntactic multiplication, which is based on the rules that are actually implemented and used in practice in automated verifiers, but that lacked formal foundation, and the semantic multiplication that has a theoretical foundation, the definition I just showed you before, but has some shortcomings. And these shortcomings have been studied in previous papers. And we present and formalize a new logic that we dubbed unbounded separation logic that corresponds to a formal foundation for the syntactic multiplication and eliminates shortcomings from the semantic multiplication. And all of our technical results have been proved in Isabelle. So let me give you 2 examples of why these 2 multiplications are actually different. Let's start with the tree, and let's see what half of a tree means semantically and syntactically. So we represent here some data structure. The notation is a bit different, but this 1 divided by 2 here means that we have half permission, so 0.5 permission to L3. We have 0.5 permission to x.right, and etc. And this looks almost like a tree, except this is not a tree because we have this node here, C3, that has 2 parents. So this is just a directed acyclic graph. And just by definition, this doesn't correspond to half of a tree semantically, because this does not correspond to a tree that we have scaled down by a half. But on the other hand, and I'll try to show you why, this corresponds to 0.5 times tree of x syntactically. And so for that, we have to apply the definition. So here the non-relevant parts are omitted. Roughly speaking, to a tree is just a right subtree and a left subtree. So if we multiply syntactically this by 0.5, we get that we need 0.5 times the right tree and 0.5 times the left tree. And we have that actually. So 0.5 times the right tree, this is what we have here, and this is a tree. There's no child that has two parents. And on the left, this is the same. We also have 0.5 times the left subtree. And we see here the discrepancy. And the discrepancy is really due to non-aliasing. When we scale down, when we use the semantic multiplication and we scale it down, we keep non-aliasing information. But when we do it syntactically, we lose it, or at least we have a more approximate version of this. So let me show again the same idea, but on a more concrete or more examples with formulas. So on the left, I have a syntactic multiplication. This is the example that we've seen before, so 0.5 times permission to L1 star permission to L2. And on the right-hand side, we have the same version, but for the semantic multiplication. And here, this is easy to see that on the right, L1 and L2 cannot be aliases. Because remember, if L1 and L2 would be aliases, we would have two permissions to the same heap location, which would be inconsistent. And even though we scale down this invalid state by 0.5, we cannot scale down anything because we don't have any state that satisfies this. But on the left, syntactic multiplication, again, removes, in a sense, this non-aliasing information. Here, L1 and L2 can be aliases. And if we rewrite this left part again using the semantic multiplication, so I just take out the 0.5 on top of the arrow here and put it semantically around the assertion, we see why the proof outline that we've shown before is incorrect. With the semantic multiplication, we don't have the right to factorization, like this is unsound. We have a fraction pi of A star, a fraction pi of B, but we cannot entail that because the right-hand side might ask for more non-aliasing information than we have. So let's recap what we've seen so far. There are two different kinds of multiplications, the semantic multiplication and the syntactic multiplication. And the semantic multiplication doesn't satisfy a crucial property, factorizability, for the separating conjunction. It, however, the reverse property, distribute, actually holds. So distributivity holds here. And for the syntactic multiplication, just by definition, both the factorizability and distributivity hold. And so far, I've talked only about the separating conjunction, but there is another important operator in separation logic called the magic wand or the separating implication. I don't have time to really go into what this is, but this is the adjoint of the star. And this is really useful to express partial data structure like a tree with a missing part. And it turns out that in this case, factorizability holds, but distributivity doesn't hold. So we have the reverse problem. And in the semantic multiplication, so the semantic multiplication has these shortcomings. But for the syntactic multiplication, we actually don't know because there was no theoretical foundation, and fractional magic wands are not supported in these automatic verifiers. And this is where the unbounded logic comes into play. So the unbounded logic provides a theoretical foundation for the syntactic multiplication in which we can prove that all of these rules work for factorizability and distributivity for the star and the magic wand, and some other rules that are in the papers, but I don't have the time to show here. So let me give you an intuition why. So we go back to the example from before. Again, 0.5 times some permission to L star 0.5 times some permission to L. And this is really informal, but to give an intuition, we have to visualize this on 2 dimensions. So on the y-axis, we have how much permission we need to L. And on the x-axis, we represent somehow the progress of evaluating the assertion. And there is this red threshold here that is put at 1 because we cannot have more than 1 permissions to a heap location. This is inconsistent. And so to evaluate the left assertion, we first evaluate the left part. And the left part says we need 0.5 permissions to L. We then add the right part and we have the whole assertion. And it shows that we need 1 permission to L. But if we do it on the right side, we have to first start inside the multiplication. So we have 1 permission to L. We evaluate everything. So now we need 2 permission to L. And this is an invalid state. So this state doesn't exist. So even when we multiply by 0.5 and we scale down the state, we also have a state that is invalid. And here is really the crucial difference between the two multiplications. They're almost the same. They arrive at the same result, but they take a different path. And for some reason, the path on the right is forbidden. And this is the key idea of unbounded separation logic. This is to say, intermediately, temporarily, we can allow states that have more than one permission to reconcile these two views. And we do that by temporarily ignoring the threshold. But we need to recover this boundedness at some point. Otherwise, we would lose key properties such as non-aliasing and the frame rule. So in a simplified manner, in a simplified description, there are two key ingredients to unbounded separation logic. First, we temporarily allow unbounded states in the assertion logic. And the second one is that we reimpose boundedness at statement boundaries. We achieve the first one by moving on from this definition of bounded states, bounded because the permissions can be only between 0 and 1, to a new notion of states where the permissions can be any fractional permission that is positive. But we need to recover boundedness, and we do this by modifying the meaning we give to Hard triples. So Hard triples, typically, the Hard triple PCQ typically means that for any state H that satisfies P, executing C in H will result in a state that satisfies Q. We add here that these Hard triples only need to hold for bounded states. And we put that on the left of an implication. So this implication trivially holds for unbounded states. And now we can use this unbounded separation logic to give a theoretical foundation for the syntactic multiplication. So the syntactic multiplication, pi times a here, corresponds to this thing on the right. And you might realize that this is exactly the same definition as the semantic multiplication. This is this intuitive definition. H corresponds to pi times a if it is a scaled-down version by pi of a state that satisfies a. And the crucial difference is between our notion of state. If you have bounded states with this definition, you have the semantic multiplication. If you have unbounded states, you have syntactic multiplication. And you might think, this is crazy, we cannot get rid of the bound, this is not separation logic anymore, but just reimposing this bound on statement boundaries, we get back the frame rule, which we have proved in Isabelle. And this is thanks to this second point. And we have proved many factorization and distribution rules in unbounded separation logic. You don't have to look at them. The ones that are important are this one, where that doesn't hold with the semantic multiplication and that enables the first proof to go through. So we can distribute and factorize over the star. And this one for the magic one, we can factorize and distribute over the star. And in particular, this shows that the syntactic multiplication can be extended to support fractional magic ones. So now we can go into these tools such as Viper and Verifast and add this construct in a relatively easy manner. So to conclude, I've shown you why we want fractional resources and how to use them. And to use them, we have 4 typical steps that we want to perform: split, distribute, factorize, and combine. And it turns out there are 2 ways to give a meaning to fractional resources: the semantic multiplication, but that has many shortcomings, and several papers have been written on this, trying to solve this actual problem by going into more complicated models. And on the other hand, there is the syntactic multiplication that works perfectly well in tools, but that didn't have a theoretical foundation, so it was built on shaky foundation. And now unbounded separation logic provides a theoretical foundation for it. The intuition of the unbounded separation logic is to temporarily allow states to have more than one permission, but just temporarily. And there is more in the paper. So we have a whole section devoted to combinability, which corresponds to the ability to perform this last step, which typically doesn't hold for all connectives, for example, for the magic one. But by going into unbounded separation logic, we can recover that property. And we also give reasoning principles to prove that an assertion can be combined. So, for example, that 2 halves of a tree can be recombined into a tree. We prove reasoning principles for inductive and co-inductive predicates, because until here in the story, I use this inductively defined predicates tree of X, but I didn't talk about inductive predicates so far, so we also have that. And we show how to use unbounded separation logic as a formal foundation for automatic verifiers. So all of the technical results have been proven in Isabelle and are available. So thank you for your attention.
Yeah. Thank you, Thibaut. There's already a question.
Thank you for a really interesting and well-presented talk. I have two questions. First one is just a brief clarification on slide 10.
Sorry?
On slide 10, you talk about a lack of aliasing information. I think you say
yes,
L1 and L2 can't be aliased. Does that basically mean you're saying that V1 and V2 are the same? Or do you mean L1 and L2?
No, so I mean...
L1 and L2 are the addresses, so you basically mean they're the same.
So L1 and L2 in this case, yeah, it's in separation logic if you have one permission to... Okay, is that clear?
And the other question, which I think is much more fun, what happens if you do allow greater than one fractions across statement boundaries?
Or what if we would remove the second part from the...
Yeah. What do you get?
No, so the question is, what do we lose? And we lose the frame rule. Because the key part of the frame rule is to say, as long as I have some permission to a heap location, I can keep the information about this. But if now another thread somewhere, or I call a method that can have one permission while I have 0.5, this method can actually modify the heap location. And then, so the frame rule would not hold, the parallel rule would not hold. So here we would really lose a lot. We would lose what separation logic is good for. Does that make sense?
Yeah, well, I don't think so. But,
Thank you.
Okay, we have an online question. Sure. What? Okay, the question is from Sören van der Waal? It's about reimposing boundedness. You quantify over bounded heaps in triple preconditions. How about post-conditions? Do you do that there too? And if not, how do we get composition of proofs?
Yes, that's a good question. So you could think that we also in a sense, conceptually, you might think that we also force that. So here for the post condition, but the technical part is that we use a semantics that doesn't have fractional permissions at all, right? And then one reason why we use a bounded state here is that if we have a state that has two permissions to a heap location, this doesn't refer to any concrete state. This cannot be mapped to a real heap. And so the short answer is that because we use a real semantics, I mean a semantics on concrete heaps, having a bounded state here and executing the semantics on an extension of this heap will result in a state that is bounded. There's no way to take, in a simplified manner, there's no way to take an unbounded state, apply the semantics, so apply a C, and then get into an unbounded state. This is, again, part of this fictional story of separation logic. So, but we could add this, and this wouldn't change anything. And in the paper, we have rules for hard triples where we say you have the right to basically add an operator to the precondition or postcondition that enforces, assumes that it's bounded.
Okay.
Yes, loud. I thought it was a fascinating talk, by the way. I'm still trying to get my head around it, but one question I had when you first put up the example was whether you could just, or whether maybe this is what you're doing, taking the fraction as basically a parameter of all your assertions. Is that
yes.
Is that effectively what's going on?
So if you look at the syntactic multiplication, this is what it does, right? But what we want is really to, so especially in tools like Viper, when you start doing things like this, you have parameters that are permissions everywhere. And this is really, in a sense, taking this concept and making it a first-class citizen, right? Instead of having to do it in an ad hoc manner, having this as a first-class citizen, and then that enables to have nice reasoning about nesting things like this. So this, in a sense, amounts to the same thing, except that now it's made as a really first-class citizen.
Well, that's what when you say first-class citizen, do you mean that the fraction is actually a parameter of the model of assertions now? Is that an extra parameter? No, it's not.
What I mean is that now you have directly a mechanism that can handle that. So you don't, when you write your definition of a tree, what you want is just to express that this is a tree.
Right.
And basically, on top of that, we give you the flexibility to take a fraction of that. Otherwise, as the user, you would have to think, how do I define this? And you would have to think about all the use cases. So this is really to ask the minimum, in a sense, in the specification to write the natural specification.
Right, right. I think we may be saying the same thing, but we'll take it offline. Thanks.
Okay, thank you.
And wouldn't it be nicer if your formula were to evaluate immediately to a fraction instead of 0, 1?
Sorry, so
Wouldn't it be nicer even if your formula were to evaluate to a number instead of 0,
so
1?
you mean going into quantitative unbounded
Of course,
separation
yeah,
logic?
yeah.
I think quantitative is already unbounded in a sense, but
Okay.
I haven't thought at all about these things. I'm new. I'm not yet to the quantitative world.
So we have one maybe last question.
Yeah, okay, so thanks for the clear talk. Are you looking at partial correctness or total correctness? And if it's partial correctness, do you think this generalizes to total correctness, or would we have to do something extra to...
Yes, so in this case, the theory is done implicitly with partial correctness, but I think it's completely orthogonal. So I think this mechanism works independently of whether we look at partial correctness or total correctness. But the theory is with active. Okay, you cannot see it because I removed the part of the definition, but it's just for any terminating state we impose the postcondition. So this is partial. So, I mean, this gets a bit technical, but it's if you want to prove someness of separation logic, concurrent separation logic, one way to do this is to say we have this fictional state here, H, that basically has fractions, but there's no fraction in a concrete heap. So what you do is that you extend it to a concrete heap that represents the heap of the whole program in all threads and everything, and then you apply the semantics to it. But by applying the semantics to it, you get, again, a concrete heap. And a concrete heap gets mapped back to a state that has only one permission everywhere. So you cannot, by applying the semantics, you cannot get unbounded states. Thank you.
Okay, let's thank Thibaut again.